And then he's finally trying to use it here, and that will potentially trigger the bug. So can someone spot the problem here? We have a lot of allocations at the beginning. Then we have the object being released, freed, and then we have the object being used. Well done, Gerard, well done. So basically, the first fact of our heap hero, which is chunk canaries, is that usually heap sprays make exploit writers dull boys. And why is that? Because the exploit was actually working. Not with 100% of reliability, but the exploit was actually working. And in fact, actually, people port the exploit to their own shellcode, just like it was, that one, and it was still working. I don't know the exactly percentage, but probably we're going to be higher than 50%. So when I saw that, I was like, why is it actually working? Because basically, as we said, you have heap spray first, object get free, object get used, nothing in the middle. So I get to spend some time trying to figure out what was going on. And then we came up, so everyone is coming up with their own concept like ROP and memory trespassing and fancy names. So we find our fancy name because every presentation needs to have one. And it's pray after free. So instead of user after free, people are doing pray after free. Why they're doing pray after free? Because these are the reasons that I find out of how the exploit was actually working. The first one, I always guess, is the most important one. Even if you're religious or not, like the exploit was working because God the Almighty was allowing it to work. Then the second one was the object was getting free, and somehow, without like any real explanation, Internet Explorer is being used quite a lot. So for a reason, it was allocated with something, and that something, by pure luck, was actually put into the meme spray. Actually, it's not pure luck, it's statistics. Like if you allocate a lot of memory and you have some trash in the middle, there is a big chance that that trash will actually be pointed to your heap spray. So that's why I guess the main reason was that. And the other one was that the free object was, the base table of the free object was actually modified only the last bytes by the low fragmentation user block offset. And we are going to explain that later. And there is actually a whole presentation about that from Chris Balasek. Balasek. So basically, this is what I found on the debugger. Like as you can see here, this is the actual function that's being triggered, the window that is being used. And as you can see, ECX is the actual, ECX. Sorry, EAX is the actual object that we free. And as you can see here, the B table, which is the first word of that object, it's something like a string, 4C41. And that, by pure luck, was actually pointing to the heap tray, and it was working. In this case, you try it again, and it doesn't work that way. Or it's a different string, or it's a completely different thing. Now, there are other problems with the debug. Let me go back again. The first thing, one of the things was that thing in the middle that was not there. Now what it was allocating and actually replacing that object. The other thing was that this guy is actually fuzzing the way he's triggering the free part. He basically doesn't know how the reference counters looks like, so he's basically just fuzzing it, which is not a good idea. Like you don't fuzz on your exploit. You fuzz to find exploits. You don't fuzz to exploit stuff. Well, he was doing it. So which is easily replaceable. Just if you are JavaScript JavaScript programmer, you just know that you can create an element and can put it there, and the element will only have one reference, because you just create it, and then you have to decrease one, and that's done. That's it. But this tells us a lot of things. The first thing is that he probably found it by fuzzing, so he didn't fully understand what's going on. He's just like put a heap spray. First he got a crash. He was like, oh, crash, nice. So now he put a heap spray at the beginning, and then he put the same stuff that makes a crash and works for him. So That's my explanation of that exploit. And that's why heap spray make exploit write null bots. Because like, okay, I put up heap spray, works, perfect, ready to go. So I have some analogies of spray after free. One of them is like going to war with a Russian roulette gun, because like one of 6 times is going to work. The other one is like looking for pornography on a chat roulette, because like 1 over 10 times, yeah, it's not going to get you what you want. Actually, this is the most decent picture I can find, because everybody was pretty bad to show it here. So how do you exploit a use after free the right way? It's actually pretty simple. The first things you want to know is to understand exactly what you are freeing. In this case, this guy was freeing a Windows. You can create your own element, and you can free it. The thing is, the first question you can ask, and that's usually on every heap overflow or heap exploit, is exactly, can it be controlled, whatever we are freeing? With control, we mean, can we send other stuff other than the window objects? And all those stuff, which are the size of those stuff? So you have to replace it. So in order to replace it, you have to allocate something of the same size. So the first question is that, can you find the size of the object? And if you can you find different objects of different sizes in order to free it? Because if you have different things you can free with different sizes, it's going to make your exploit even better than it usually is. But in my case, I was not able to find other objects. Basically, the object that was being free was what is called a tier-off object or tier-off interface. So basically, each JavaScript object on mstml.dll, either a document, a Windows, an element, etc., in JavaScript had a representation which is based on a tier-off object. A tier-off object is basically a wrapper of all the other objects. It has as, lost the word, sorry. So basically, the objective of the tier-off, is to basically to create an object and maintain the reference to that object. That was the word. So, but the problem was that I can only send to that function, to the set attribute value, only a tier-off object. No matter if I send an element, a Windows, a document, whatever object it is, it was always a tier-off object. And a tier-off object has a fixed size of 28. That was easy to find. If you have symbols, it has a create tier-off interface, and you get the size. Now that you have the size, you have one important thing. Now you have to replace, whenever you free that size, that object, which is 20 bytes long, you have to replace it with something else. And now you usually will go to the Alexander Sotirov heap tree and try to do one of these things that he do. But the problem is that the JavaScript strings has the following format. It has first the first D words as being a D word of the size of the string. And obviously, the first D word is actually the B table of the object. So if you replace the B table, you're replacing the B table with a size, which is usually not good. So that was not an option. The option was to find an alternative way to have a complete control of the object or the allocation. And in our case, we basically, we try to keep everything related to one DLL. So in our case, we were planning to do everything related with MSHTML DLL. And so basically, we target the element properties and method. But there are many other ways. For example, one of the exploits that we did some time ago, it was using the EXML server that is inside JavaScript, just by doing like the object.open, and instead of the URL, using a string. That was actually allocating a real string in a real memory. So by sending like 28 bytes, you get to allocate what you want and controlling obviously the first 4 bytes. So this is how we did. Basically what we did was we reverse engineered the getDistID function and the invokex, which were part of MS-HTML. And we found out that every element inside MS-HTML has an interface which is inherited from C element and at the same time from cbase. And cbase is actually that has the real getThisID function and the invoke X. Remember that those functions are the ones that allow you to resolve methods and properties. So the idea was like, okay, let's try to understand how this resolution works, and let's try to find out which are the functions that allow you to set a property or call a method. Because obviously, they are not as simple as a common ActiveX object. A common ActiveX object usually have the symbols, have like a put something, and that means that it's the putter function of that property, or you get slash something, and you know that that is the getter of that property. But in the case of elements, it was completely different, because if we were using the same interface to resolve all the elements. So again, this was inheriting from cbase, and basically the only requirement here was that you need to override the method getClassDescription. This is inside getThisID. Once you replace the getClassDescription, you basically have to return a pointer to a desk structure, which, this is annoying, but I'm going to say it, has a pointer to HDLLsec, and at the same time, the HDLLsec structure has a pointer to a structure which is called string table aggregate. Sorry. And this string table aggregate has two pointers, which are two string tables. The first one is the one related with the method and the property that every element share between each other. And the second one, the one we have the X, is usually replaced by the name of the element. So if it's like a body element of the body tag, we see like C body string table. So in this string table, there is a lot of pointers to structures that has all the information about each of the properties. And obviously, getThisID from cbase and invokeX use that structures quite a lot. So again, our objective is to find out exactly for each method or for each property which exactly function is using, so we can analyze that function and see if that function is actually allocating a controllable string or other stuff. Obviously, this is very useful from an auditing standing point, because you can audit all the setter and getters and methods from the elements. So basically, each pointer on that string table has a pointer to this structure, which is the associate table structure. This holds another pointer to the prop description. This is basically the structure that holds all the information of each method or property inside an element. And what you see here, for example, you have the hash, which is a hash of the string, which is used to find the string fastly through that structure. And then you have a couple of index in here, which is a byte long. They are indexed into a big table. The function one is the one that has the index for a function table, which is the one responsible for actually doing the getter and setter or calling or the actual method. And the UID is related with the UID of that object. So it's like the body, it will be the UID of the element object for body. And then on the property description, you have the actual name or an alternative name of the property. And then you have a lot of flags we are not going to explain. And you have this keyword here, which is called WIMP function, which is basically an offset to another big table of functions, which are the invoke functions. Invoke function, basically, what it does, we can see here in code, which is easier. There, basically, we have first the index to the UID, and that will give us the actual UUID of that element. And then with that UID, we do a query interface, which, as you guys has already said, the query interface is the one that returns interfaces. And so we're going to get the actual interface of that element. Because remember, the getThisID and the invokeX are both a very generic function for all the different elements. So if they are adding new elements, instead of writing the raw objects, it's just adding those stuff there. And then we have a function index, which was on the WIID index function. And then, first of all, it actually calls an invoke function, which is the one that